right, lesson 10.1. So bear with me on the lesson 10, chapter 10 lessons. They're a little long. I wouldn't say difficult by any means, but they're long. There's a lot of information. So you probably want to have these notes with you to kind of follow along, okay? That's partly why I put the printouts there, okay? So chapter 10 is all about circles. All you could probably ever want to know and more, okay? All about circles. So we start with tangents to circles and something called arcs and chords in 10.2. Also, be on the lookout for your chapter 9 test, okay? 9.7 was supposed to be Tuesday's class, right? So you would have gotten your test on Wednesday today, but I want to give you guys a little bit of time to process. So maybe look for it tomorrow. Tests and quizzes will go up, but once they are due, I am taking them down. Remember, you got to stay on top of your tests and quizzes. Unique situation we're in, okay? So lots of communication with me on if there's any confusion, okay? I'm available to answer questions. I can, however we need to do this, okay? So back to the lesson. So 10.1, tangents to circles, right? So we start by defining a circle, okay? A circle, and this is in your notes that are on Google Classroom, okay? Set of all points in a plane that are equidistant from a given point called the center. So here's point P. So any point that is the same distance from P is going to be on the circle. So here's our circle, okay? These points are all the same distance from point P. They should be. Looks a little off, but if you were to use your compass, that's why you have that distance, okay? It's the same. So we're going to call this circle P, or we can write out the word circle P, okay? P is the center, it's the middle, all points are equidistant. Given a circle, we can have a radius, we can have a diameter, okay? The radius is the distance from the center to any point. So we would say that these are all considered a radius. So one is a radius. Talking about more than one radius, it's called a radii, okay? And they're all the same distance. So two circles are congruent if they have the same radius. It means they're going to be the same size, okay? Then you can have a diameter. And a diameter is the distance across the circle through the center. Okay, so when we look at our circle up there, right, diameter would be from here to here because it's passing through the center. So a diameter happens to be 2 radii. Okay, so twice the radius. All right, so radius and diameter. Then, so you can also measure a radius and a diameter, okay? They are measurable segments. So a radius, its endpoints are going to be on the circle and the center, and then a diameter, the endpoints are going to be both on the circle, okay? Then we can have a chord and a secant. All right, so a chord is just a segment whose endpoints are on the circle. A diameter is an example of a chord, but just have to have endpoints being on the circle. So this could be a chord, okay? Doesn't have to be through the center. And then a secant is just going to be a line that intersects the circle in 2 points. So a chord has endpoints. A secant doesn't necessarily have endpoints. So a secant could look like this, okay? Doesn't have endpoints to it. And then I forgot you have a tangent as well. Okay. And a tangent is a line that just touches your circle in 1 point. So, put it on here. This would be a tangent. It's intersecting right here at one singular point. Okay? All these definitions are in your notes. Sometimes it helps just to have them explained to you and visually see them. Okay? So a radius from the center to a point. The diameter goes through the center. Endpoints are on the circle. A chord just has endpoints on the circle, not necessarily through the center, okay? So a diameter is a chord, but not all chords are diameters. And then a secant and a tangent. So secant intersects in 2 places, tangent intersects in 1. Okay, so those are our main definitions for circles right now. We're going to focus a lot on tangents to the circle. Okay. So we're going to look at that image that we have, right? So here is a circle, and then we have a line going this way, line going this way, then one coming down like this, and then another one like this. So here is A, B, H, E, that's on the circle. This is also on the circle at F. Point G is here. Here is I. C is the center of our circle, and point D. Okay. The first question is asking about segment AH. So here's A, here's H. So this segment here, right, it's intersecting our circle in 1 place. So AH is a tangent. All right. Then we're looking at EI. So here's point E and point I passing through the center. So the line segments that pass through the center connecting 2 sides of the circle are called a diameter. It's a chord, but we want to be as specific as possible, so that's a diameter. Okay, then DF. So D and F, both are on the circle. DF does not pass through the center, so this is a chord. And then lastly, CE. Okay, well, C is the center, E is on the circle, so CE is a radius. Right? Not the only radius, but a radius. So just kind of seeing some of our definitions there. Okay? All right. First part. This you need to look at when we're coming up here in a minute. You're going to need to look at your book, right? On page 596. Okay, I'll tell you what to look at in a minute. So we're looking at the top of the page if you're looking there. When we have two circles in a plane, okay, you can have two circles that intersect in two places. So two circles intersecting twice. You can have two circles intersecting in one place, so something like this, or even something like this where one is inside the other. And then you can have two circles that don't intersect at all. So not intersecting, or one completely inside the other, okay? Pretend they all look even, right? I know they don't, they're kind of odd looking circles. Okay, so 2 points of intersection here, 1 point of intersection, and no points of intersection. Two circles can't intersect more than that. That's it. Okay, 2, 1, or none. So something like this, these would be considered concentric circles where they're completely inside of each other and they share the same center. Okay, this is what we need to look at, though, more specifically. So two circles that intersect in one point are called tangent circles. So these are called tangent circles. Okay, they are called tangent circles because you can have a line that is tangent to both circles at the same point, right? So these two circles, they're tangent because they intersect in one point. You can have a line that's tangent to both at that point. Would look like that. Two circles that intersect in one place have a common tangent. That's what this is called, okay? All right, this is the definition I need you to look at. An internal tangent versus an external tangent. The book has it backwards, okay? So an internal tangent is when the tangent line is in between the two circles, okay? So a common internal tangent intersects the segment that joins the centers of the two circles, right? So here's a center, here's a center. That's the segment that connects them. So this is an internal common tangent. An external tangent does not intersect the segments that join the centers. So here's the center and center, right? The tangent is not intersecting it, so it's called external. It is outside the two circles, okay? The book has the pictures correct. No, the pictures are backwards. The definition is correct in your book. Yeah. So in the book, right, we're looking right here. This is what I want you to look at. This is backwards, okay? Common internal tangent intersects the segment that joins the centers of the two circles. Well, that would be here. This would be your internal tangent. This would be your external. So the definition's good, the picture is not. So just keep that in mind if you're looking at your book. All right. So tangent lines, okay? Tangent means they intersect in one place. All right, 2 theorems. Okay, so we're going to kind of just look at, instead of writing it out, since you should have it, okay? We are theorem 10.1 and 10.2. We're talking about the point where the tangent line intersects the circle, okay? It's called the point of tangency. So if you have a line that is tangent to a circle, here's our circle, okay? This line is tangent. It is intersecting in one point. Then it has to be perpendicular to the radius at the point of tangency. So tangent and the radius are perpendicular. All right. Then the converse of that, right, says that if a line is perpendicular to the radius at its endpoint that's on the circle, then this line is tangent. So the converse of this. This says if it's tangent, then it's perpendicular. This says if it's perpendicular, then it's tangent. Okay? Recall that perpendicular means they form a right angle. We've done a lot with right triangles. Chances are you're going to use your Pythagorean theorem. Okay? So looking at an example, right? So here is our circle. E is our point of tangency. We have a line here that is tangent to the circle. D, or we don't know if this is tangent, sorry. D is the center. So DE is your radius. We want to know if CE tangent to the circle. Okay? So if it is, that means that this would be a right angle. Okay? So that's what we have to ask ourselves is, to answer this, is CE perpendicular to DE? Because DE is a radius. So if it is, that means that angle E would be right. So how do we decide, given a triangle, if we have a right angle? Well, the Pythagorean theorem. So 45 is the longest side. So we're going to say is 11 squared plus 43 squared equal to 45 squared. That's a 45. Okay, well that's 121 plus 1,849. Does that equal 1,970? And it does not. Okay, so no, CE is not tangent to the circle. If they were equal, then yes, it would be tangent to the circle. Okay, so that's how we check to see if we have a tangent line. If it was tangent, this would be a right angle. Okay, all right, next. So from a point on a circle's exterior, you can draw 2 different tangents to the circle. Okay. So that's what theorem 10.3 is talking about, okay? So here is our circle. Here's a point outside the circle. We'll call it point S. So from point S, here's circle P, we can draw 2 different tangent lines. So we would have one tangent line going this way and one tangent line going this way because they both intersect the circle in one place. Okay, we'll call it point R and point T. So if, and actually this would keep going this way because they're lines, okay? So it's saying that if 2 segments from the same exterior point are tangent to a circle, so if this is tangent and this is tangent, then the segments are congruent. So then we would be able to say that SR is congruent to ST. Just the segment itself, not the whole line, because we don't measure lines, right? So we're talking about here, this segment and this segment would be congruent if they're both tangent from the same point. Okay? All right. That's all of your theorems for 10.1. So then let's do our proof here. Yeah, let's do our proof. We're still practicing those, right? Not near as many proofs, but you still got them. Okay, so we're told, that's our given, that CB is tangent to circle A at point B, and CD is tangent to circle A at point D. Guess what we're doing? We're proving two triangles are congruent. Triangle ABC is congruent to triangle ADC. Okay? So here's our picture. Here's point C, B, and D. So we're saying that these are tangents. Here's circle A. Okay? So what we're trying to show is triangle ABC is congruent to triangle ADC. Okay? Well, let's think about this, right? So A is the center, B and D are on the circle. So that makes AB and AD each a radius. And all radii are congruent. So these are congruent. So we're going to just make a little note here. AB, AD are radii. So they're congruent. Right? This is how we're kind of working through this thought process here. Then, theorem 10.3 tells us that if a line is tangent from this, if two lines are tangent from the same exterior point, they are congruent. So then that tells us that this is tangent and this is tangent. They're both tangent from the same point outside the circle, so CB and CD are congruent. So that's theorem 10.3. So they're congruent. Okay, well, then CA is congruent to itself by the reflexive property. So side, 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 our triangles are congruent. Now we just have to write it as a proof, okay? So let's just put our statement and our reason, right? So we know that CB is congruent to CD because theorem 10.3, they're tangents. Okay? Then AB is congruent to AD because they're radii. And AC is congruent to AC because of the reflexive property. Then that's all you need. You have three sides. So ABC is congruent to ADC by side, side, side. So we've used our circle to make a proof about a triangle. And that is tangents to circles.